Hi everyone. In the previous lecture, I spoke about Grant-Schmidt orthogonalization procedure. I made a small mistake when explaining that. So I said there was a problem with this equation rho 1 in the previous class. Okay, there is no mistake here. The equations are perfectly fine. So that's what I wanted to say right now. Okay. Then in the previous class, I confused rho 1 to be the correlation factor, so which is not true. Rho 1 here is just the projection of, so if I take S2 of t and project it onto psi 1 of t, that's your rho 1. So to understand what projections are, so I'm just going to give you already a familiar example. So let's say we take the two direction vectors x cap and y cap, two-dimensional direction vectors. Then I said any vector in the two-dimensional space can be represented as a linear combination of x cap and y cap. So let's say this is A, B. Let's say this is the vector z. So z can be represented as A x cap plus B y cap. Now if you see here, A here is the projection of z onto x. So that can be computed by taking, you take the vector z and take a dot product with x cap. Okay, you are going to get A. So it's very similar to this. Rho 1 here is nothing but the projection of S2 onto psi 1. So that can be obtained by taking the inner product of S2 with psi 1. Okay, so when I take inner product of S2 with psi 1, I am going to get rho 1. So then rho 1 into psi 1 of t will be the vectorial component of, or you can see the signal component of S2 along psi 1. Now I can write A x cap is the x component. It's a part of the vector z. Okay, it is that component of vector that lies on the z x axis. Okay, on the x direction. Okay, so A here is the projection. That's what I made a small mistake thinking that it is correlation, and I asked you to divide it by the energy of S2. That's not true. So you can ignore that. So the few minutes of the last lecture, you can completely ignore it. So this equations, whatever is given here, is perfectly fine. And I've already discussed about how to go about talking about deriving the Grant-Schmidt orthogonalization procedure. You start with n signals, and you can derive a basis set psi I of t, where I going from 1 to L, and I said L will be always less than or equal to n. Okay, you can derive a set of orthonormal basis functions, whose order, number of the bases, the dimension order is going to be always less than the number of signals you began with. Why are we doing this? It will slowly become clear in the next lectures or in the coming lectures. So now that I'm done with that, so I'll start with our discussions on digital communication. So we began with the discussion of digital communication. We saw how to convert analog sources to discrete bits. So you eventually converted it into bits, and sometimes we said we just have data files as bits to transmit. Okay, so you have a transmitter and a receiver, and in between there is a channel. So that's the general model of a communication system. So you have a transmitter and a receiver. Now the problem we thought was that because the channel is continuous, it's an analog channel, you have to transmit this waveform, whether it's wireless or wired, the channel is always analog. Okay, so therefore you need an analog waveform which you can actually transmit across the channel. So that analog waveform, which means what I need to do is I have an m bit of data. Okay, and this m bit of data, we said we are going to convert it. There are 2 power m possible combinations for this m bits. So I'm going to call that as capital M. So you will have 1 to m waveforms. You will actually generate m analog waveforms, and then output one of those m waveforms depending on the m bit code. Okay, at the receiver you will be receiving that one of m analog waveforms whose duration will be 1 symbol interval. Okay, so these one of m waveforms are called symbols. Each waveform is now called as a symbol, and each symbol contains m bit of information. You should keep that in mind, because it will tell you what is the value of these m bits. The symbol is going to contain that information. So again, last class we discussed symbol rate is 1 by ts, bit rate is going to be m by ts, small m by ts. That's your bit rate, where ts, I'm sorry, I've just used t here, ts or t, I'll just go by what I say verbally. So this is t, let me maintain uniformity. So t will be your symbol rate, M by T will be your bit rate. Now at the receiver, you are going to receive an analog waveform. So you have transmitted an analog waveform with in the duration 0 to t. In the receiver, you are going to receive the waveform 0 to t. So how does the receiver know that you have transmitted this waveform? So that's the next question. So now the receiver has to make a decision, okay, in the presence of, for example, if the channel had nothing else to do, the signal will, whatever you transmit, it's going to come out exactly at the output. But channel has its own bandwidth limitations. In addition to that, you're also going to add noise. Okay, so your signal is now going to be corrupted by noise. Now the problem is, the receiver's problem is, how am I going to detect what was transmitted in the presence of noise? So this problem is what we call signal detection in the presence of noise. So in the presence of noise, how am I going to detect a signal? So to solve this, I'll just assume a very, very simple modulation scheme, which is pulse amplitude modulation. Okay, and in pulse amplitude modulation, I'm just going to take the simplest model, which is 2PAM. Again, just to quickly mention some points here, whenever I write MPAM or MPPM and MPWM, the M here represents to number of levels. So number of bits is going to be log of M to base 2. This will be your small m. Okay, M here normally represents the number of levels of any modulation scheme. Okay, and the number of bits is going to be log M to the base 2. So that's something to keep in mind. Now I'll take the simplest case of 2PAM, which means I'm going to have only 2 levels, which means I can only represent 1 bit. There is only 1 bit of information in one symbol interval. So where T here is your symbol interval. If for bit 1 I'm going to transmit plus A, bit 0 I'm going to transmit minus A. Okay, so now what I'll do is, I'll do the entire analysis on signal space. I'll tell you why am I doing that. First, I'm going to do this analysis in signal space. So we know if I have a signal, for example, what is the symbol energy? So there are 2 symbols here. I'll call it ES1 as the first symbol's energy. That's going to be A square into T. That's going to be same as ES2, the second symbol's energy. Now there is something called average symbol energy. If you want to compute the average symbol energy, that will be simply summed over probability of, in this case, probability of symbol SI, where I going from 1 to M, into ESI. ESI here, the symbol's, ith symbol's energy. Okay, this will be your average symbol energy. Okay, so once you know the average symbol energy, you can find the bit energy by dividing it. If you know the symbol energy, I'll call it EABS. Okay, you have to just divide it by the number of bits. So log M to base 2, you will get the bit energy. Okay, so this is a quick calculation of just some things that very, very simple basics that you have to keep in mind. The next step is, how am I going to detect signal in the presence of noise? Now what I'll do is, I'll draw the signal space diagram for this. So now we have a signal which is 0 to T with an amplitude A, and we can very easily find psi 1 of T. I'll simply take the signal and divide it by the energy of the signal. The energy of the signal is A square, root of energy of the signal. I have to divide it by the norm of the signal, remember. So norm of the signal is going to be root of energy, which is root of A square T, which will be A root T. So if I divide it by that, I'm going to get 1 by root T into P of T, Pt of T, where Pt of T is a pulse of duration T seconds starting from origin lasting till T seconds with an amplitude 1. This is your psi 1 of T. So your signal, I'll call it S1 of T for bit 1. Bit 1, for a bit 1, I'm going to call it S1 of T, will simply be A root T. Okay. If I multiply bit 1, I want to represent bit 1 in terms of psi 1 of T. You can simply take the projection of S1 onto psi 1. So you just have to multiply these 2 signals and integrate it over a single cycle. If I multiply and integrate it, I'm going to get A by root T integral 0 to T 1 dt. Okay. I mean, I've taken all the Pt of T is just 1, and A I've taken it as common out. So you will get A root T. Okay. So what I'm getting here is A root T. Now A root T is nothing but square root of energy. right? That's the square root of energy, symbol energy. So I'll call it E as the energy of the signal. So that will be root E times psi 1 of t. So that's the projection you have found. The projection of the projection of the signal is root E in this case, and psi 1 of t. And similarly, you can very easily show S2 of t, it's for bit 0, the signal is going to be minus root E psi 1 of t. And the dimension, again, we discussed for PIM, dimension is 1, it's just 1. So on the signal space, I am going to represent psi of t here. This is your origin E. The first point, it's going to be plus root E, and the other signal is going to be minus root E. So this is bit 1 and this is bit 0. This is S1 and S2. This is two signals. Now, I am going to assume that somehow you receive only root E. How will you receive root E? Now, what I am going to do is, I am going to actually take this input signal and I am going to multiply it with psi 1 of t. See, now you know the waveforms at the receiver, at the transmitter. Okay, you know what waveforms you are transmitting, and the sender also knows the waveforms. So from this, he has the knowledge of the basis functions of the input you transmit. Okay, so what the receiver is going to do is that as soon as you get send the waveform, he is going to multiply it with project onto psi 1. So what you are going to get here, so let's say somehow he is able to do this. How is he able to do that? You might need some circuits to do that for you, but let's say you are able to do that now. Or in a digital system, you will have some other ways of doing it. I'll talk about it later. But let's say this mathematical operation is somehow you are able to do that. So you will first multiply it with psi 1 of t and integrate it from 0 to t. The output here, it's going to be root E if S1 is transmitted and minus root E if S2 is transmitted. Okay, but you should keep in mind what I am going to receive here is not just S1 of t, but there is also noise present with the signal. So this part of the receiver is called correlation receiver. Okay, it's also called a correlator or a correlation receiver. So it's called the correlation receiver. Okay, I'm going to correlate the input signal with a basis function. What I'll receive then will be either plus root E or minus root E. Okay, now I'm going to receive S1 plus n of t, and there is what I'm trying to say here is that this plus root E will be the output if only you transmitted S1, but there is also noise transmitted along with the signal. So then what you are going to receive is that you are going to get something like this, root E plus, I'm assuming S1 is transmitted. So if depending on S1 or S2, I will get plus minus root E. So this is 1 or 2. Depending on S1, 2, you will get plus minus root E. And integral 0 to t n of t into psi 1 of t dt. So this is nothing but the projection of noise onto the orthonormal basis function psi 1 of t. Now I will not go into the mathematics of this. See, when you integrate it and find this value, you are just going to get one variable. You are just going to get some value at the output. Okay, I am not going to go in depth into this, into the analysis of this. All I can say is that since the energy of psi 1 is just 1, okay, all I can say is that you can treat the value you are going to get as, see, let's say this is plus minus root E, plus I am going to receive n, a value called n. Now this is a random variable because noise is random, right? So this value, I am saying the integral value under this, because noise is random, when I integrate it, I am going to get a random number, a random variable. This noise is a random variable. Now there is a little bit of mathematics which can actually very easily show that the mean of this mean is expected value of n is 0, and the variance of this will be, variance is sigma square is given by n naught by 2. N naught here I have discussed in the last class, the units is watts per hertz. Last or one of the previous lectures I have discussed, or even in the classes, the unit is watt per hertz. There is a proper theory for it. We need at least 4 or 5 lectures on a topic called random processes to discuss what is this, but right now you can just take this as a fact. Okay, so this is your received vector. Now what you are going to receive at the receiver is this. You are not only going to receive the signal part, you are also going to receive the noise with it. Now I'll just draw the constellation diagram and then show that. So if this is plus root E and this is minus root E. Now, one of the simplest way the receiver can work is that the receiver can just be a threshold detector. It will just say, okay, if my signal is 0, is greater than 0, I'll assume S1 is transmitted. If it is less than 0, then I'll say S2 is transmitted. But the problem is, this is also accompanied by noise. There is root E plus N, minus root E plus N. There is also noise. Then you can't exactly say what you have received. You can only say with a certain probability, because it's a random variable. N is a random variable now. Which means now we have to know what is the statistics of N. Now, for most of the signals, we assume the statistics of N always turns out to a good degree of approximation, and it has well been proven and all that. And it turns out to be a Gaussian random variable, especially noise, because of thermal noise. The noise which is arising because of random movement of particles, it's called thermal noise, charged particles, and that generally obeys a Gaussian distribution. Okay, so now you're supposed to know what a Gaussian distribution is in this course. I'll write a general expression for a Gaussian distribution. A Gaussian distribution with a finite mean mu and a variance sigma is given by 1 by root of 2 pi sigma square it's a function itself, so in e power minus of x minus mu the whole square by 2 sigma square. So this is the expression for a Gaussian random variable. The properties of a Gaussian random variable is, if I integrate the Gaussian random variable for its entire time of existence, the value of the integral will be equal to 1. This is true for any random probability distribution. Okay, this is for a continuous probability distribution. Similarly, for a discrete probability distribution, you can define probability of x equals xi, where I varying from all the possible values of I will always be equal to 1. Sum of all the outcomes, probability of all the outcomes equals 1. That's a very simple result. So this is a continuous random variable. So for a continuous random variable, the point values make no sense. If I ask you to find what is the probability that, say, x equals or x lies in this range, what is the probability that x is within this range? So x is within this range x minus delta x by 2 to x less than x plus delta x by 2. If I ask you, you simply have to integrate it from minus delta x by 2 to plus delta x by 2 and find the value. So if I take this Gaussian random variable, if I ask you to find what is the area under this curve, it will give you the probability. So if I make shrink x to 0, if I ask you what is the probability at a single point, then delta x becomes 0, then the probability also becomes 0. So for point values make no sense. Point values, the probability of occurrence of a single event is going to be 0 for a continuous probability distributions. Okay. For a discrete, that's not the case. Discrete functions do exist. Okay, discrete variables, it's only single valued outcomes, so you can define a probability for a single outcome. But in a continuous variable, random variable, you cannot define probability for a single variable, but rather for a range of variables. Okay, range of possible outcomes that x can take. So the Gaussian function that we are interested in, generally noise tends to have 0 mean. Okay, so the Gaussian function that we will encounter is the one with a 0 mean and a variance given by sigma square. So that will be simply 1 by root 2 pi sigma square e power minus x square by 2 sigma square. Okay, and there is something called as, this is the probability density function or PDF. Okay, PDF is the probability density function. The next is CDF, cumulative density function. That is nothing but integral minus infinity to x fx of x dx. This is x is just a variable here. I can call fx of t dt also. Okay, so this is nothing but if you take some probability distribution function and integrate it from minus infinity to some value x. Okay, so that's called CDF, cumulative distribution function. So that cumulative distribution function is always positive because probabilities are always positive, and it will keep increasing from 0 and eventually it will reach 1. Okay, the final value. So if I take, I will call it C of x equals this. C of 0 will be 0 and C of infinity will be 1. Okay, so C of minus infinity is actually 0. So for a Gaussian random variable, if you look at the Gaussian random variable, it is symmetric around the origin. Okay, so which means the probability that x is greater than 0 is half, and probability of x less than 0 is also half. So if I ask you C of 0 is nothing but the cumulative probability that the C of x is simply probability that x is less than or equal to x. Okay, so where x being 0 here. So that's, I think I should define it that way. Your C of x is probability of x less than or equal to x. Okay, that's a cumulative distribution function. And for this, it will be probability of x less than or equal to 0, and that will be simply half for a Gaussian random variable or any random variable which is symmetric around the point or mu here, I should or the origin here. If it is, say, it is symmetric around 0, then your C of 0 will be equal to half. So your CFF, the function will actually touch half here, and it will start from 0, half, and eventually the peak value will be 1. Okay. There is one other very important function we need to know before we start doing the analysis. It's called the complementary error function, or Q function, Q of x. Okay. The literature you might find ERF or ERFC. So complementary error function and error function. So I'll talk very briefly about this, but in this course you just need to know what is Q of x, the definition of Q of x. Q of x is defined for a Gaussian variable with a variance equal to 1. Here standard deviation sigma square equals 1. So the definition of Q of x goes this way. It's integral x to infinity fx of x dx. So where fx of x here is a normal distribution. So if I take a Gaussian distribution, it can have any non-zero mean and any variance sigma. If I assume your mean is 0 and your variance is 1, then we call that as a normal distribution. Okay. So written as n of 0 comma 1 means that it is 0 mean, this is mean, and this is variance equals 1. Now for a normal distribution, the mean is 0 and variance equals 1. And the Q function is defined for a normal distribution with a 0 mean and a unit variance. It's defined as Q of x equals integral minus infinity to x 1 by root 2 pi, because sigma square is 1, into e power minus x square by 2 dx. Okay, I'm sorry, this is integral x to infinity. So if you take x and then integrate it, so it's called the tail probability function. Okay, so you find the area under the tail of a Gaussian function. So this area will be your Q function, and this is defined for a unit variance, Gaussian random variable of unit variance. Okay. Now, keeping this in mind, we will go back to this problem of signal detection. Now, I said we had a receivers of a type wherein we'll take your orthonormal basis function and correlate it with your received signal in the presence of noise, and then we will compute 0 to t, multiply it and compute its integral. That's what I call correlation. Here, at this point, if I am going to sample its output at instant t equal to kt, I am going to sample it at the end of t. What I am going to get here will simply be root of e, or plus root of e if I transmit S1, or minus root of e if I transmit S2. So this is S1, S2 I am going to get minus. Plus there is also noise which is corrupting it. So this is the main problem. If there was no noise, then detection is pretty simple. I mean, there was nothing to detect. If you receive any positive, you are going to say, plus S1 is transmitted. But the problem is always in the presence of noise. What is noise going to do there? Now I will go back to the constellation diagram, the signal space diagram. So the signal can be shown as 2 points in the signal space diagram. Here now, if it looks very similar, what the values I am going to receive is plus minus e. It's very simple because I have projected it. I have projected the signal onto psi1. What I am going to receive will simply be the coordinates on the signal space diagram. Okay, I am simply going to receive the coordinates. Now in the presence of noise, this guy previously was supposed to just be localized to 1 point if in the absence of noise. In the presence of noise, it can be anything. Now this noise can take values all the way from minus infinity to plus infinity. Of course, the probabilities of plus and minus infinity, it's going to be negligibly small, but still it can take any value. Now the receiver, what we are going to do is that we are going to put a threshold here. It's called a thresholding receiver. We will just put it at 0 and say if what I received here, if my received signal R here, I'm going to call it R, is greater than 0, I'm going to say S1 is transmitted. If R is less than 0, I'm going to say S2 is transmitted. That's it. So now I said what we discussed a few moments ago is that the noise variable we know which has 0 mean and a variance given by n0 by 2. I'll simply call sigma square as the variance right now. Then what I'm going to receive in effect will actually be, if I'm going to write it, it's actually going to be spread like this. Maximum what I'm actually drawing the probability density function, okay, for the received signal. So this is actually, I'll call it PR. P capital R of R. R is the random received random variable. See, because what you're receiving is actually plus minus root E plus noise. Noise is a random variable, so R also becomes, this is deterministic. But since noise is random, our received signal will also be a random variable. Because it's a random variable, you should be able to draw its probability density function. Okay. If S1 was transmitted, so this will be F R given S1 is transmitted of X is going to be this. The probability distribution function, if S1 is transmitted, the mean is going to be plus root E. Okay. And variance is going to remain the same. Variance is unaffected. Similarly, if S2 is transmitted, the mean is going to be minus root E. I mean, you can easily compute. How do you compute mean? Expected value of R equals X. This is not a random variable. So that's, if you find the mean of a constant function, you will get the same variable as it is. So it will be plus minus root E, and mean of expected value of n is 0. So the mean of E of R is equal to plus, depends on, if S1 is transmitted, it will be plus root E. S2 is transmitted, your mean of R is going to be minus root E. Okay, your decision region is here. Now why did I choose the decision to be 0? I'll come to that little later. Here I'm going to assume they are equiprobable symbols, meaning the probability of S1 being transmitted is same as probability of S2 being transmitted, and that's equal to half. And similarly, the graph is going to look something like this. Okay, I haven't drawn it properly, but okay, this is your graph for the probability density function for the received signal. Now, when will we say that there is an error in reception? So I need to say probability of error is when you have received S1, you have transmitted S1. Sorry, if I transmit S1, the probability of S1 is the probability of transmitting S1. Multiply it with probability of receiving S2 given S1 is transmitted. Okay, given S1 is transmitted, which means this is your PDF, given S1 is transmitted, this becomes your PDF. Then you have to find out what is the probability that you will think that S2 is received. Now you said thresholding here, the reception threshold is 0, which means if I want to find the probability that if this was transmitted and the receiver is going to think it is S2, then your error must be you lying somewhere here, which means the noise variable you added, it has created so much of error that your error is lying in this region. So then you just have to find what is the probability that your noise lies in this region. Okay, and how do you find that? So I'll assume, see, from origin, this is the Gaussian function, this is the center. From the mean, you have to move a distance of plus root E. To make the analysis even simpler, I'm just going to assume that the distance between the 2 points, instead of root E, I'll assume D as the distance between the 2 points, and I'll call it D as 2 square root E. Okay, D is your 2 square root E. E here is your symbol energy, symbol S1's energy, and which is same as S2's energy. So let's say this is your point. So this point, the distance between the 2 points is going to be D. So the distance from origin to this point will be D by 2. So this will be minus D by 2. The distance is going to be D by 2. The distance between the 2 points is going to be D. Okay. So what is the probability that your Gaussian function is going to lie in this region? It's simply, I'm going to stay at this point from mean. I have to advance a distance of D by 2. So this is equivalent to finding the area of a Gaussian function. I'll say at origin, and if I move a distance D by 2 and find this area. Okay, so that area integral is going to be integral D by 2 to infinity 1 by root of 2 pi sigma square, because this is a noise variable with the variance of sigma square, e power minus of say x square by 2 sigma square dx. So this is your probability of receiving S2 given S1 is transmitted. Okay. Now to evaluate this integral, if you look at it, I am going to compare this to your q function, which is 1 by root 2 pi integral d by 2 to infinity e power minus, as I said, it is just q of so this is q of x here, so this will be, the point here will be x to infinity e power minus t square by 2 dt. This is the expression for q of x. X here refers to this x, the x here refers to this x here. So can I somehow express it in terms of q? So this integral doesn't have a closed form expression, but we will express it in terms of q. For that you have to numerically compute its value, and it is readily available. You can need any standard textbook will contain the value of q for different values of x. So now this function, I am going to make a substitution in this function here, so which is 1 by root of 2 pi sigma square integral d by 2 to infinity e power minus x square by 2 sigma square dx. In this function, I am going to make this substitution x by sigma as t. So you get dx equals sigma dt. So you make that substitution and you will simply get root of 2 pi. So the limits is going to be d by 2 sigma to infinity e power minus t square by 2 dt. So sigma will cancel out and finally you will get this. This is nothing but q of d by 2 sigma. So your probability of S2 being received given S1 is transmitted is this. In a very similar manner, if you are asked to find, this is minus d by 2, what is the probability that S2 is received given S1 is transmitted? Same way you have to compute the trail probability of error. This is the 0 is the thresholding point. So you have to move a distance d by 2 from here, and that will also be q of d by 2 sigma. This is the same area, so it's going to remain the same. So your probability of error is going to be probability of S1, which is half here, into q of d by 2 sigma plus probability of S2 into q of d by 2 sigma. Okay, and S1 and S2 are same, so which is half. So you'll simply get q of d by 2 sigma as the probability of error, where d is the distance between the 2 points in the signal space. It's essentially the Euclidean space between the two signals, Euclidean distance between the two signals. Okay, so that will be your expression for probability of error. Now this function, if you plot it, so this term d by sigma is what we call d by 2 sigma, is what we call it as the signal to noise ratio, because d contains information about, so if I actually write what is d, d is simply 2 root e. So if I substitute that in this expression, I am going to get, and sigma is actually, sigma square is n naught by 2. Okay, so if I take d by 2 sigma, this will be 2 root e upon 2 into n naught by root of n naught into root 2. Okay, so you will be left with root of 2e by n naught. So this will be your q of root of 2e by n naught will be your probability of error. So this value e by n naught by 2, this is your noise power, this is your, you can treat it as signal power. See, you should actually, if I ask you to find the signal power, the power for this is 0, of course, okay, because it's just existing for t seconds. So the relationship between power and energy, normally if you divide power by t, you get energy. Okay, so power has these units of if you divide energy by t, you get power. Okay, so if you see, power actually has these units of watt, or energy will simply be, energy can be written as power into time. Okay, so this is nothing but watt per hertz. The units of energy is watt per hertz. So now I can say that there are two ratio of watt per hertz. So if I ignore the hertz, then this is actually very similar to signal to noise ratio. See, when you compute signal to noise ratio, you have to actually consider signal power divided by noise power. Noise power, this is noise spectral density. N naught by 2 is the noise spectral density. You have to actually multiply it by 2 bandwidth to get the noise power. Okay, the units of N naught by 2 is watt per hertz. Multiplied by hertz, you are going to get watts. Okay, that will be your PN. But I am saying this is very closely related to the signal to noise ratio. Okay, so normally what we do is you can treat it like Q of SNR, approximately, and this is again approximate result, or the general actual expression is root of 2E by N naught. Okay, so in this case, bit energy for a binary PAM, bit energy is equal to symbol energy, because your symbol, because it's just 1 bit information, so symbol energy will be equal to bit energy. So sometimes they write it as 2EB by N naught. If I plot this function as a function of EB by N naught, EB by N naught here is called the signal to noise ratio. So then I am going to get a graph like this. It's like a waterfall. Suddenly it will just going to signify, what does it tell you is that if you increase EB by N naught, there's an exponential decrease in probability of error. So this probability of error I can achieve of the order of 10 power minus 6, 10 power minus 12 for this high speed wireline data transfers between the servers in Google and all that. You need very high, very low bit error rate. Okay, this term is called bit error rate, PE, because it's a digital communication, and this tells you approximately how many bits are in error. So when it is 10 power minus 6, 1 in 1 million bits are in error. So if it's 10 power minus 12, it's actually trillion, 1 in 1 trillion bits are in error. Okay, so the less probability of error you need, the higher should be your signal to noise ratio. Luckily, to get a very low probability of error, you don't need to burn, even if you just double it, you are going to get an exponential increase in probability of error. So that's a very important thing. That's the big advantage you will get here. If you recall from your previous lecture, if you want to increase your Shannon capacity, which is your BPS, bits per second, power was not really helpful, because even if you increased your power exponentially, there was only a marginal return. There was law of diminishing marginal returns, if you recall. But if you increase your SNR on the other power on the other hand, the bit error rate will go down exponentially. That's the main difference. You may not gain in terms of speed, but you will gain in terms of reduction in probability of error. So these are the points to keep in mind. So what we discussed so far is that we discussed a method to actually receive a signal, and we call it the receiver as a correlation receiver, and this receiver performed better in terms, this is called as an additive white Gaussian noise channel, AWGN receiver. So your noise is just an additive noise. So we said that noise is just added to the signal at the receiver, and this noise is because of channel and also because of the receiver circuits. The circuits in the receiver will introduce its own thermal noise. Okay, so this is an optimum receiver for an additive white Gaussian noise channel. Now I'll very quickly finish a small discussion regarding this. What I discussed in the previous, few moments ago, is that I assume the thresholding, the point of threshold, say this is minus root E or minus D by 2, and this is plus D by 2. I assume that the threshold, receiver threshold, was already at 0. I didn't say Y should be at 0. Okay. Now how do you find the threshold? What should be my threshold for this receiver? That is determined by the simple relationship. Your goal is to minimize your probability of error. At the receiver, you should have minimum probability of error. That should be your goal. If you want to have minimum probability of error, then what should be your thresholding region? Let's say I'll take the simple case of binary symbols. I've transmitted 2 symbols. What should be my threshold such that the probability of error is minimized? To write that, let's assume it is not 0. The threshold point is not 0. Instead, it is, say, epsilon away from 0. Okay, now I have 2 Gaussian random variables here. Noise is still the same, but I'm trying to find what if the thresholding point is slightly away from 0. So I'll call probability of S1 as the P of PS1 as the probability of S1, and PS2 as the probability of S2 being transmitted. Then the probability of error is going to be probability of S1 into, okay, now you should keep in mind probability of S2 given S1 is transmitted. Now what is that? So if you take your Gaussian random variable, you will have to integrate it from, this is I'm showing, instead of 0, instead of moving from D by 2, you will have to move D by 2 plus epsilon, and then find the area under this integral, area under this curve. Okay, so that's simply going to be Q of probability of S1 into Q of D by 2 plus epsilon by sigma. So if you recall, if it was exactly at origin where epsilon was 0, the probability of error was q of d by 2 by sigma. That was your probability of error. But now because we have added epsilon to it, it's going to be, it's actually going to be d by 2 plus epsilon by sigma plus probability of S2 into, now since your threshold point is not at origin but rather it is at epsilon away from it, for S2 the area of integration will start from, if you can very easily show that for S2 if you move say d by 2 minus epsilon from here, that will be point where your threshold is applied. So it will be q of d by 2 minus epsilon by sigma. Now this is your probability of error. Now your error is a function of epsilon. What is the ideal value of epsilon should I choose? That's the question. Now if you look at this expression, just to quickly cover some basics about the q function. Q function is nothing but for a norm, again q is defined for a normal random variable with mean 1, mean 0 and variance 1. This is the area under this curve which is x to infinity. Q of x is 1 by root 2 pi integral x to infinity e power minus x square by 2 dx. This is your expression for q of x. Okay. Now c of x, I said, is cumulative distribution function which is 1 minus q of x. So you can see c of x is actually complementary to that, complementary to what q of x is. So this will be c of x, the area under this. Now the total area we know is 1. So if you take c of x and add it with q of x, I am going to get 1. So your q of x will actually be 1 minus c of x. If you recall, we already discussed that your c of x, if you differentiate, if I want to find dq of x by dx, okay, so you should understand q of x is nothing but it's the area tail probability function. So if I increase x, the area is going to reduce, which means the slope is negative, all right, the value of q is reducing with if I increasing values of x, so the slope is negative, so it should be negative. So what you will get is minus of fx of x, where this is a unit, it's a normal distribution denoted by the symbol with 0 mean and variance as 1 with a minus sign, negative of this. Okay, so I'll quickly apply this for this expression. So that will be probability of S1. I'm going to take probability of error and differentiate this with respect to epsilon. Now this is q of d by 2 plus epsilon by sigma. If I differentiate this with respect to sigma epsilon, I'll get fx of x. So that is nothing but e power minus of d by 2 plus epsilon by sigma the whole square into half, right? It is e power minus x square by 2 into 1 by root 2 pi. So there is actually 1 by root 2 pi here as well. So I'll write it as root 2 pi plus probability of S1, S2 into, there is a minus sign here because the slope, as I said, it's minus of f of x, the slope is negative. Okay. So fx of x is simply 1 by root 2 pi. See, what I have written here is fx of x is minus 1 by root 2 pi e power minus x square by 2. So this is the slope of q of x. Okay. And this again, in the second term again, there will be a minus here with e power d by 2 minus epsilon by sigma the whole square by half. But now you have to keep in mind here, epsilon is subtracted from d. So if I increase epsilon, this value is going to reduce, d by 2 minus epsilon will reduce. So in this case, the value should actually increase, the slope should be positive. So that's why we will actually get again by root 2 pi. I mean, you can simply solve this using chain rule of differentiation as well, but this will be plus here. So that one more minus again would cut here, you will get it plus here. So finally, you will get an expression like this, probability of S1 e power minus d by 2 plus epsilon by sigma the whole square into half is equal to probability of S2 e power minus d by 2 minus epsilon by sigma the whole square by half. Again, I will just take ln e, log to base e on both the sides. So I am going to get ln of probability of S1 by probability of S2. Okay. And I will take this term to this side. So I will get d by 2 plus epsilon the whole square minus d by 2 minus epsilon the whole square. The whole square, this entire thing multiplied by 1 by 2 sigma square. So this expression will reduce to 4 d by 2 epsilon into 1 by 2 sigma square, and you will simply get epsilon d by sigma square. So the value of epsilon is simply going to be equal to, if I substitute in this, I will get sigma square by d into ln of probability of S1 by probability of S2. Okay. So if they are equiprobable symbols, probability of S1 and S2 are equal, then epsilon will simply be equal to 0. So the region where we are going to cut the threshold, okay, so this is say d by 2 and minus d by 2. For equiprobable symbols, the center, the exact distance equidistant from the two symbols should be your point of threshold. So that's what this analysis told us. Only then you will get minimum probability of error. For non-equiprobable symbols, so this is say S1 and S2, you have to keep it slightly away from the origin. And that should make sense, because for example, let's assume S1 is occurring most of the times. Let's say its probability of S1 is 999 by 1000 and S2 is just 1 by 1000, which means almost all the times you are going to get only S1. So instead of choosing this as the threshold, if I choose this as a threshold point, some other point away from it, because if you remember, your q of x is going to significantly reduce if you increase the value of x. The slope is exponentially reducing. If you recall, the slope is e power minus x square by 2 with a minus sign proportional to this. So which means it's going to exponentially reduce. So your probability of error will also exponentially reduce. So if I'm going to multiply it with a large value times a very, very small value, okay, and then whatever the q of that function, I have not written the full function here, plus probability of S2 is going to be very small, so I don't mind making this slightly larger. Okay, since the probability is so small, it's okay, I can do that. I'll eventually get a small probability of error. So that's what this analysis told us. So the threshold point will actually be, okay, this epsilon for it need not be exactly at the center, is all I'm trying to say here. So again, when you receive two signals, they need not be in the same axis. I mean, for example, let's say the symbols are actually orthogonal to each other. I have received two symbols with constellation points here. Then your constellation region will always be, you just have to draw a line joining the two symbols. The constellation point, the decision region is going to be perpendicular to the line joining the 2 points. So if your symbol is in this region, let's assume this is S1 and S2, you'll assume S2 is transmitted. If it is in this region, you'll assume S1 is transmitted. So which means the probability of error, whatever be the dimension, it will only depend upon the distance between the two constellation points. That's a very important thing to remember. Okay, that it just depends on the distance between the two constellation points, and that will be q of d by 2 sigma. For if let's say we just have two constellation points, it is simply the standard result for equiprobable symbol, it is simply q of d by 2 sigma. Okay, this is the optimum value and you are going to get this number. For other things, for non-equiprobable symbols, you will have to compute it using this result. Probability of S1 into q of d by 2 plus epsilon by sigma plus probability of S2 into q of d by 2 minus epsilon by sigma. So you have to use this to compute your probability of error. For equiprobable symbols, it's pretty simple, it reduces to this. Okay, so it's independent, whatever be the dimension, it can be two. In fact, these 2 points can be 2 points in an n-dimensional space. Even then, the only thing that matters to you is the Euclidean distance between the 2 points, which is d here. It depends only on d and sigma. Okay, that's the thing to remember. It remains the same. If it's equiprobable symbols, then it is simply q of d by 2 sigma. They can be any in any n-dimensional space, the probability of error will remain the same. Okay, so that's what we have discussed so far. We have discussed how to transmit a digital symbol using different modulation schemes, and we've also discussed how to receive a digital signal in the presence of noise. Okay, so that's what we call optimum receivers in the presence of additive white Gaussian noise channel. Fine, and there is just one other point which is called as matched filter receivers. I have discussed that in the class. I think it will become more clear, especially matched filter receivers will become much better, much more clear if you actually look at it from frequency domain point of view. I have explained that intuition in the class, so I don't think I will cover that here. Okay, so because I want you guys to attend classes as well, so that point I will not explain it at this point. Okay. So I'll discuss the remaining things in the next class, in the next video.